Welcome to Conceptual Physics at Delaware Tech, Chapter 26, Properties of Light. So in this chapter, we'll cover electromagnetic waves. So when we say light, we mean all types of light, anything from radio waves to gamma rays. And that is the entire electromagnetic spectrum. So we'll talk about each of the different types. We'll talk about transparent materials and opaque materials. These are transparent to visible light, or opaque to visible light. These are the wavelengths of light that humans can see. Then we'll talk a little bit about the structure of the eye and how the human eye and the human brain work together to see, and some of the tricks that happen with optical illusions. So electromagnetic waves, these are vibrations that have both an electric field and a magnetic field running perpendicular to each other along the length of this transverse wave. And these waves all originate from accelerated motion of charged particles, usually electrons, and we'll just mostly keep it to electrons for this course. But when electrons are accelerated into motion, so they get faster, they get slower, these will generate electromagnetic waves that can be studied. Okay, so these waves can interact with other particles. So you have particles that are moving fast, they get accelerated, and a wave is formed. So you have photons of light of any wavelength, any frequency. These are all types of light along the electromagnetic spectrum. And these waves of light can also be thought of as particles, what we call photons. So light of all types can be thought of either as waves or as individual particles, and sometimes it's more convenient to think of them as particles, and sometimes it's more convenient to think of them as waves. They really are a combination of both, and I know that doesn't make sense to what we see in the macroscopic world around us, but things are different when you're dealing with subatomic particle sizes. But these waves can interact with other charged particles like other electrons or other parts of atoms, or even the electrons in bonds of atoms, and they will exert a force on those. So electromagnetic phenomena is composed, as I mentioned, of both an electric wave and a magnetic wave that move together as a single wave. So here's an example of an electromagnetic wave, and you see that there is an electric field shown in red here, and that's the wave in the electric portion of the wave. And then you have a perpendicular wave of the magnetic field shown in blue. And they run perpendicular and they're to each other, but they are also perpendicular to the direction of this double transverse wave. It's a transverse wave that has two parts, but they're intimately involved with one another. They run together. And it's these vibrating fields, these alternating fields in both the electric and the magnetic realm that produce this electromagnetic wave. And all electromagnetic waves in a vacuum, whether we're talking about radio waves, microwaves, infrared, visible, ultraviolet, X-rays and gamma rays, they all travel at the speed of light, which is about 300 million meters per second. Okay, that's essentially almost that's almost the distance from the Earth to the moon in 1 second. It takes light about 1.25 seconds to reach the moon. So light is incredibly fast, especially in a vacuum. All right. So if an electron vibrates up and down 1,000 times each second. So remember what per second means. That's hertz. Remember the unit of frequency we talked about in previous units. 1,000 times each second, that is a frequency of 1,000 hertz, 1,000 vibrations every second. It will generate an electromagnetic wave also of 1,000 cycles per second, 1,000 waves per second, 1,000 vibrations per second, 1,000 hertz. So which of the following is true? It has a period of 1,000 seconds. It has a speed of 1,000 meters per second. It has a wavelength, that's what the lambda is, the Greek letter for L, of 1,000 meters, or none of the above. Well, let's think about this. We know the frequency of the wave will match the vibration of the electron. It's changing It's changing speed and direction, so that will generate an electromagnetic wave that matches the frequency of 1,000 hertz, 1,000 per second, 1,000 seconds to the minus 1, or 1 over a second. Any of those are the same unit. So if you want the period of a wave that has a frequency of 1,000, the period is always 1 divided by the frequency. So 1 divided by 1,000 would be 1,000th, or 0.001 seconds. So A can't be right. That amount is the amount for the frequency, but it's not the amount for the period. The speed, it's an electromagnetic wave. It's moving at 300 million meters per second, so 1,000 can't possibly be right. And the wavelength of 1,000 meters. Well, if you remember in previous studies when we were looking at sound, we learned that the velocity of any wave is equal to the frequency times the wavelength. So frequency times wavelength equals speed. But that also means the wavelength equals the speed divided by the frequency. Well, we know the speed is 300 million meters per second. We know the frequency is 1,000, so instead of 300 million, we take out 3 zeros, it's 300,000 meters is the wavelength, so 1,000 doesn't match either. So none of these are true. So we know the vibration is 1,000 per second, meaning a frequency of 1,000 hertz. The period is 1 divided by that, 0.001 seconds. The speed of all electromagnetic waves, at least in a vacuum, is the speed of light, about 300 million meters per second. It's exactly 299,792,458 meters per second, but we're going to round it to this easy number of 300 million meters per second. And then using the formula that the wavelength is just the speed divided by the frequency, 300 million divided by 1,000 is 300,000 meters. So none of the above are true. And you should be able to take any one piece of information and figure out all the other characteristics of a wave using this. So let's look at the electromagnetic spectrum, the whole broad category of what counts as an electromagnetic wave. Your textbook will frequently use the word light to mean only the visible light range, but physicists will frequently use the word light to mean anything in this entire electromagnetic spectrum. So the classification of a wave in the spectrum is based on the frequency. It can also be based on wavelength, but more often it's based on frequency. And you'll notice the lowest frequencies on here are the radio waves and the microwaves. But if you look at the number of the frequency, they range from 10 to the 3, 10 to the 4, 10 to the 6, 10 to the 8th just for radio waves. In other words, the slowest radio waves are 1,000 hertz. They may even be slow. They may even be a lower frequency than that. So they're already really big numbers. So radio waves get up to almost 1 billion hertz, 1 billion cycles per second, and that in electromagnetic waves is considered a really low number. That sounds strange, but look how big they get on the right side of this graph. So radio waves are the lowest frequency, the least energetic of all the waves. Energy is directly proportional to frequency. So if I say less energetic, it also means lower frequency. Microwaves are next. So they're a little more energetic, a little higher frequency. If you go up, you get to the infrared. We call it infrared. Infra means below. So it's literally below the red color of the visible spectrum. You know, you have the rainbow, red, orange, yellow, green, blue, violet, indigo. Okay, that range of colors that has the lowest frequencies at red and the highest at blue and indigo, blue and violet and indigo. If you go lower than red, it's below red or infrared. If you go above violet, it's ultraviolet or beyond violet. So you probably heard these words many times. You didn't realize that they literally say what they are. Infrared is below red. In other words, we can't see it. It's below the visible wavelengths that we can see, the colors of the rainbow. And ultraviolet is above that. So we have the visible light, and the lowest frequency of visible light is the beginning of the rainbow, red. And the highest frequencies of visible light are the blue, indigo, violet. Those are the highest frequencies of light, the highest energy of visible light. So these are, if you look at this chart, you see visible light is a tiny little sliver of the entire range of the electromagnetic wave scale, all right, of the wave spectrum. And after that, we have ultraviolet. And ultraviolet is a pretty good range here. And there are various ultraviolet groupings. Sometimes you'll hear UVA, UVB, even UVC. These are the different groupings within the UV range, and they kind of overlap. And these are more energetic, and they'll actually cause damage to your skin. They'll cause damage to your DNA. So we have to be careful when we're out in the sun, not because of the visible light, but because of the ultraviolet light and the rays that are more energetic enough to start doing damage to the molecules in your body. And then the highest frequency electromagnetic waves are the X-rays and gamma rays. And these overlap a lot. When you start learning more physics and more chemistry, you realize the only difference between X-rays and gamma rays are where they come from. They're really the same range of frequencies, the same range of energies, the same range of wavelengths, but they're the highest energy electromagnetic waves. If these energy waves come from electrons, we call them X-rays. If they come from the nucleus of the atom, we call them gamma rays. But they're really the same ray, the same energy levels. Okay, and there are no sharp boundaries between any of these. Visible, we have a pretty good idea, but people vary from one to another. So somebody might be able to see slightly lower wavelengths than another person. Slightly lower frequencies than another person, or slightly higher frequencies than another person. So, but all of these can overlap depending on where you're studying. So microwaves and radio waves have an overlap, microwaves and infrared have an overlap, et cetera, et cetera. They're not hard lines about where the divisions are. So here's another graph that shows you a little bit bigger, and you can take a look at some details of the electromagnetic spectrum. And you can see you have a wide range of radio waves. And if you look on the bottom, it's the energy, but we're going to look the second from the bottom, the frequency. So this is the waves per second, otherwise known as hertz. So you see the radio waves start maybe 10 to the 5th, 10 to the 6th, 10 to the 7th. But by the time you're up to gamma rays and X-rays, you're at 10 to the 21 or 10 to the 20, 10 to the 20 or 10 to the 21 cycles every second. That's how many waveforms are flying by. The whole wavelength is flying by 10 to the 20 of these per second. That's an incredibly high frequency, and because of it, they have huge energies, and they can be quite damaging. You do not want to be hit with even ultraviolet light, let alone X-rays for any period of time, or gamma rays for any period of time. Obviously, we get X-rays, we get CAT scans, but those are very limited blasts of X-rays, and there are definite health rules about how much exposure you can get to these rays. If you want to remember the order from lowest energy to highest energy, from lowest frequency to highest frequency, and by the way, it's inverted for wavelength. Wavelength and frequency are inversely proportional. So you'll notice the wavelengths are the biggest for radio waves and the smallest for gamma rays. But if you want to remember this order of radio waves, microwaves, infrared, visible, ultraviolet, X-ray, gamma rays, there are a lot of mnemonics online you can look up. I kind of pieced one together from 2 or 3 different ones that I found. Rich men in Vegas use X-ray glasses. So rich, radio, men, microwaves, in infrared, Vegas, visible, use ultraviolet, X-ray, and glasses, gamma rays. So it's an easy way to remember the order in case you're having trouble with it. All right, the electromagnetic spectrum spans waves ranging from the lowest to highest frequencies. The smallest portion, in other words, the narrowest range on the entire electromagnetic spectrum, is that of A, radio waves, B, microwaves, C, light waves, or specifically visible light waves, and D, gamma rays. Well, if you remember, Visible light waves are the narrowest range because they're defined by what the human eye can see, the colors we can see. And if you look back at that spectrum, you see there's a wide range for radio, a wide range for microwave, a wide range for infrared, a wide range for ultraviolet, for X-rays, for gamma rays. The only thing that doesn't have a wide range is a little sliver of the electromagnetic spectrum that is the part that our eyes can actually detect. Anything lower, we can't see. Anything higher, we can't see. Which of these is fundamentally different from the others? Sound waves, visible light waves, radio waves, X-rays. Well, remember, visible light, radio waves, X-rays, as well as gamma, ultraviolet, infrared, microwaves, these are all part of the electromagnetic spectrum. They're all different versions of the same kind of wave. But sound waves are completely different. So the electromagnetic spectrum has all these different versions here. I just read them off: radio waves, microwaves, infrared, visible, ultraviolet, soft and hard X-rays, and gamma rays. And those are transverse waves that don't require any medium to fly through. In other words, they don't require any matter. In fact, they move faster on average through a vacuum. But sound waves absolutely require matter, number one. And number two, they are pressure waves, mechanical waves, meaning they involve mechanical motion of whatever they're going through, like air or even rock. There's movement of the atoms in compressions and rarefactions, and that's what the waves are. Instead of going up and down or side to side like the transverse waves are, this one is compression, rarefaction, compression, rarefaction. And that's what we call the longitudinal waves. And sound is a perfect example of longitudinal type waves that require matter. They absolutely require matter, whereas the electromagnetic spectrum, the electromagnetic waves, they can work in matter, but they work better with no matter at all. All right, so what happens when light starts interacting with matter? Light is transmitted similarly to sound. I just finished telling you how the waves are very different, but they are still waves. And being waves, they're due to vibrations, and the vibrations will move through whatever they're traveling through, either empty space or air or water or glass or rock or diamond, whatever they're traveling through. Some waves can pass through, like gamma rays can pass through most everything. But visible light, we're going to talk about visible light because we're talking about transparent materials. And when we say transparent, unless we say otherwise, we're talking about visible light. So these are materials that visible light can go through. And the classic example of that is glass. Plain old window glass that you have in your homes, your apartments, your schools, your work. And how do we know they're transparent? Because we can see through them. So light must have gone through from the other side, gone through the glass, and reached our eye. Otherwise, we wouldn't be able to see images on the other side of the glass. And so light these are waves due to vibrations, and they will travel, and you can think of them interacting with particles, charged particles, especially electrons in atoms. And when they interact with atoms, they interact especially well if they match the natural frequencies of the electrons in those atoms. So you can think of it like tuning forks here, where if you hit one tuning fork and you've got another one just sitting over there that has the same frequency, maybe they're both 440 hertz, this one's 440 hertz, and you hit this one, it starts producing waves, pressure waves, longitudinal, compression and rarefaction waves of sound through the air, and those waves hit a new piece of matter, the tuning fork, and that's its natural vibration. It's the vibration it prefers to do based on its size and structure. Well, the same thing happens with light hitting electrons. Sometimes light will hit electrons and it doesn't match it, and it will do certain things that we'll talk about. And other times it will interact with it and completely resonate that natural frequency and pop it up into a higher energy level. So when light strikes a substance, there are a number of different things that could happen. There are several different outcomes, really 3 or 4 depending on how you count them. It can either just bounce off, and some people will describe this as a quick absorption and a release. If you talk to really high energy physicists who are doing very advanced theory, they say it actually never gets absorbed. It's just bouncing off, and that's reflection. And that's pretty easy to understand in those terms. When you actually look at the details, it's really tricky and weird. But we're going to just assume reflection is you hit it and you bounce off, and the light isn't doing much interacting with the matter. But you can also have light being absorbed by the matter, and so it might be absorbed by the electrons. So when we say this, we're talking about photons of light, particles of light, little packages of light we'll call photons. And you can, like I said, you can think of light as waves, or you can think of it as particles. In this case, it's easier to think of it as particles. So the particles come to the electron, and if they match that energy of the electron, the natural frequency that the electron likes to vibrate, it'll interact with the electron. The electron will absorb that corpuscle of light, that particle of light called a photon, and jump up to a higher energy level. And it might stay there and eventually be turned into heat just by heating up the molecule that it's part of and the electrons that it's part of, and just making them vibrate more, and that extra movement becomes heat. Or it can and quickly just dump it out because it's not the resonance frequency. It's not the right matching frequency. And we'll talk about examples of that. So you have two different versions of the absorption. It either absorbs but quickly gets rid of it, or it absorbs it and it pops it up to a higher energy level that eventually becomes heat. And then the third way is it just passes right through and doesn't do anything to the matter. Okay, so let's talk about transparent materials like glass. In glass is made of silicon and oxygen atoms. We refer to it as silicon dioxide. It's usually made from quartz. People take sand, which is essentially ground up quartz on the beach, and you heat it up, you melt the sand, and it just becomes this mess of silicon dioxide molecules, and then you let it cool quickly so it doesn't have time to make beautiful crystal structures like in quartz. But when it does that, it comes together and it forms all kinds of bonds in no particular orientation, no particular lattice structure like you would in a crystal. We call this amorphous, meaning without shape. And that's what glasses are. Glass is an amorphous solid. It has no actual molecular pattern in it. It's just bonds between atoms, and silicons are all bound to oxygens are all bound to silicons, but it's a big mess. All right. So you have this glass, which you can even think of as a gigantic molecule, but we're only looking at the individual atoms. And it turns out these electrons in the glass, in these atoms, they have very specific energies that they resonate, energies that the electrons like to absorb, will make them vibrate just enough so they pop up to a higher energy level and maybe eventually turn into heat. The problem is visible light, the light we can see, is not a high enough energy, not a high enough frequency to do that. So what happens is, if you look at this diagram on the bottom and you look at it, see how it's part A, B, C, D, E, F, G. If you start at A, you see what happens is the little package of light, the photon, hits the first atom. And the atom absorbs it for just a second, kind of realizes it's not the right frequency to bump it up to the next level. It's not high enough energy. So it spits out a different photon, because that photon's gone. It absorbed it. It produces a new photon because it's vibrating a little bit. And remember, vibrating electrons can release photons of light, release electromagnetic energy. Well, whatever energy hit this within the visible spectrum, so if it was red light or blue light or green light, whatever it hit it, that's the same frequency it's going to spit out, and that'll go and hit the next atom that's in its way, or the next electrons of the next atom it's in its way. And it'll just keep doing this. It'll absorb, one atom will absorb it, it'll realize it's not the right energy, spit it out, the next one will absorb it, not the right energy, spit it out, and it's all the same frequency, it's all the same wavelength all the way through, but it's different photons each time. It takes one in and creates a new one, takes one in, creates a new one, takes one in, and that one creates a new one, and eventually a photon is released on the other side of the glass. And it looks exactly like the photon that went into the glass, but you've already exchanged photons along the way. You've absorbed them so they're gone, and then created a new one and then absorbed that one and then created a new one. So they're different every time, and they go through, but eventually they come out and it looks just like the same stuff. So it's confusing to anybody looking at the characteristics before and after. They look identical, but they're not exactly the same particles. All right, so the electrons enter the glass very briefly. They're absorbed quickly. They cause the electrons to vibrate, but not high enough energy, so they pop them out. Now, a small percentage will stay in there and make the molecules vibrate a little bit, and that is heat. Okay, anytime you have motion, that's kinetic energy. That is essentially the internal energy of a substance, and internal energy in this case means heat. Heat, when we measure something with a thermometer, what we're really doing is measuring, we think of it as measuring heat, but what temperature really is to a physicist is just an average speed of molecules either moving or vibrating. The more they vibrate, the more they move, the higher the temperature. So by making them move more, you've increased the temperature of those particles. So a little bit of that light doesn't get through. Some of it is used to make heat, about 2 to 4%. About 90, sometimes 95% of the light will make it through all the way to the other side. It won't be the same photon, but it'll make it through. Now, if you look at these numbers, you realize they don't add up to 100%. There's also a few percent, maybe 4%, that's reflected off the glass. It never even enters the glass really. It just hits the outer surface and bounces out. So there's always a little bit of reflection. There's a little bit that's turned into heat, and there's a little bit that just gets all the way through the glass. Most of it gets through the glass, I should say. All right, so now, because these absorptions, these quick absorptions and quick release of a new photon and then a new absorption or a quick release of photon, those take time. So as a result of this absorption and then reemission and then absorption and reemission, you end up with a lower average speed of the light going through something like glass relative to a vacuum. A vacuum has no particles doing that. The photons will just go through straight until they hit something. But in the glass, they're going to be captured and spit out. What's interesting, though, is the speed between electrons when it's been gulped up and then spit out. That period of time that it's traveling, even within the glass, that speed is exactly the same as the speed in a vacuum. Our classic C of the speed of light, C, 300 million meters per second. The reason why light is slower on average going through the glass, and we refer to it as the average speed of light in glass or in water or in air or in a diamond, is because of this repeated gulping and emitting and gulping and emitting, absorbing and emitting until the light makes it all the way through. But that takes time for that absorption and that reemission to happen. But once it's traveling, it's always traveling at only one speed. Photons can only travel at one speed, and that speed is about 300 million meters per second. It's the average speed that might be slower within some type of matter. Okay, so we've talked about visible light, and this will happen. So visible light, if it starts with a red beam of light, that's within the visible range, it'll end up a red. If it starts as purple, violet, it'll end up as violet. If it starts as green, it'll end up as green. Same frequency, same wavelength going through. And that's what visible light does of all types of visible light. And that's why we can see all the colors through a piece of glass. But ultraviolet light, so higher energy, and infrared light, lower energy, lower wavelengths, lower energy, lower frequencies, those don't get through the glass, and for two different reasons. So ultraviolet light is more energetic than visible light and has higher energy. And remember, I told you that visible light will excite the electrons, but not enough to bump to a new energy level. Well, ultraviolet light is high enough to bump the electrons so that they vibrate at their own natural resonating frequency. So it's enough to kick them into a higher energy level in the atoms that they're at, and the atoms now get more energetic. And as a result of this higher energy, eventually that will be dissipated, but in the form of just vibrations and heat. So ultraviolet light will never make it through the glass. It's captured and then kind of dissipated into heat. It doesn't get through. So we say that glass is opaque to ultraviolet light. In other words, it can't get through. whereas glass is transparent to visible light. Visible light can get through. And now if you look at the lower energy, the lower frequency light below red, the infrared, we can't see these either. These are frequencies that are lower. And in this case, the energy is not high enough to do the exciting of the electrons like visible light does, or the really big exciting like ultraviolet does. But it can start exciting the bonds, the electrons in the bonds between atoms, the bonds themselves, or even the whole atoms. That may seem counterintuitive, but you need higher frequencies to get some of these smaller particles. And now we're looking at bigger parts of the molecule. So the infrared can start vibrating and resonating with bigger parts of this, and it starts making the whole molecules, the whole atoms and the molecules that it's part of within the glass, it starts making them vibrate. And that vibration is essentially kinetic energy, which is the internal energy of the system, which means it will increase in temperature. So infrared light essentially makes glass warm up. It doesn't get through either, but for a different reason than UV. And because of this, infrared light is frequently called heat waves. If you've ever been to a restaurant, especially buffets, you'll see these red lamps sitting over top of your food in the buffet table. They look red because there's some visible red wavelengths coming out that you can see with your eyes, but a lot of the wavelengths coming out you can't see. They are lower frequency, they are higher wavelength than we see the infrared. Infrared's lower frequency, lower energy, higher wavelengths, and these are not wavelengths we can detect with our eyes, but that radiates down onto the food, vibrates the molecules of the food, especially the water in the food, and will keep the food hot. And that's why we use these for heat lamps. All right, so just to review, with glass is not transparent to ultraviolet. Ultraviolet is high enough energy to excite those electrons into the next level, so the glass electrons get excited to the next energy state, and then eventually it's released as heat slowly. Visible light, it does interact, but it doesn't interact well enough to stick around, so it gets passed right on out with exactly the same frequency, exactly the same wavelength that went in. So if it went in as orange light, it would come out as orange light. If it went in as white visible light, which is a collection of all the colors, white light is all the colors of the rainbow together. We perceive it as white light. It'll come out as white light, all the different wavelengths and frequencies of visible light. But if it's infrared, it's too low a frequency. So if you look at the diagram down at the bottom, you see it's not as tight, it's not as many waves, so it's a lower frequency, but the wavelength is bigger. That's an infrared. So the higher the frequency, the more of these, the shorter they are, the shorter the wavelength. That's how you remember which way it works. So one goes up, one goes down. But infrared will just heat up the atoms and the molecules and just make them vibrate and resonate, which just makes the whole thing warm, and they never get through either. Okay, so we talked about average speed, so let's look at some comparisons here. So in a vacuum, the speed is about 300 million meters per second, if you want to know the exact number, and this is the exact number because in 1982, the governing body of standards and measurements for the entire world decided they were tired of people remeasuring the speed of light every year and everybody having to change all the measurements and all the calculations based on the speed of light. So they had already gotten to something like this number in blue with a lot of decimal places after it. And eventually they said, this is crazy. Every year we have to change all our calculations. Let's just set the speed of light to the nearest integer, 299,792,458 exactly meters per second. There's nothing after that, okay? And you don't have to know this. I thought it'd be an interesting story. But you might say, how can you possibly do that if that's not the speed of light? Well, what they did was they changed the size of the meter. Now, the meter was already measured very accurately, but you'll notice this is already 9 decimal places in this number, 9 digits in this number. So changing the length of the meter, you are only changing the 10th decimal place of the size of a meter. So it's a very small change to anybody in the regular world. that are measuring something with a meter, they never notice it. But the physicists were much happier with always having the same exact value for the speed of light. So this was set in 1982, and this is always going to be the speed of light for people on Earth. All right. In the atmosphere, you've got air molecules. You've got 78% of our air is nitrogen gas, 21% of our air is oxygen molecules, nitrogen molecules, oxygen molecules. Then you have a little bit of the remaining 1%. It's argon and water vapor and carbon dioxide and CFCs and a lot of other trace gases. But most of it's nitrogen and oxygen, and the light will interact with them, and it'll spit it out, just like it does with glass, because it's not the right wavelengths for visible light. And as a result, it's only slightly slowed down in air because there aren't that many molecules to interact. It's not like glass that's a solid that has a lot of atoms packed in together with a high density. They're spread out in air. So the effect of going through an atmosphere is only a tiny, tiny percent. It's 0.03% slower than the regular speed of light in a vacuum. So thus, instead of C, it's 0.9997 C, almost the same thing. Water will have a significant effect, though. Water will go it down to about 3/4 of the speed in air, excuse me, in the vacuum. Now, keep in mind, the speed between air molecules or between water molecules is always going to be C, the 300 million up at the top here, meters per second. But the average speed of going through this are these slower speeds of 0.75 C for water, 0.67, so about 2/3 of the speed in most glasses. And it's going to depend on what type of glass you're using. And by the time you're at diamond is denser and what we call optically denser. So it slows down light even more because it's capturing and releasing, and it really slows it down. So it's only about 41% of the vacuum speed. So that's a lot of stopping and starting of the photons within diamond, and it slows it down tremendously. And because of this slowdown, you'll learn later in chapter 28 that it causes bending of light when it enters the diamond from outside from the air, and it bends the light, and because of that bending, it starts reflecting inside the diamond, and that's why diamonds are so sparkly, because of all the light bouncing around on the inside of the diamond trying to get out. Okay, so strictly speaking, the photons, okay, we're talking about the particles of light instead of thinking of them as waves. The particles of visible light incident on the glass, that means hitting the glass, are the same ones that travel through and exit to the other side, not the same ones that travel through and exit the other side, absorbed and transformed into thermal energy, or D, diffracted. Well, we already talked about the fact that the figure we looked at, you can see they're absorbed and released, absorbed and a new one is released, absorbed and a new one is released. So by the time they're actually released out the other side of the glass, those are completely different photons. And that tells us that it's not the same photons that went in. But the frequencies are exactly the same, the ones coming in and the ones going out. So if you have a certain color of visible light, it's the same color going through. If you have white light, which is all the colors going through, it'll be white light going through, all the colors going on the other end. As far as absorbed and transformed to thermal energy, that's what happens with infrared light. It's absorbed by the molecules. It vibrates the whole molecules and turned into thermal energy. With ultraviolet, it's absorbed, popped up into higher energy levels, and then slowly transformed into thermal energy, into heat as well. So C is what happens to infrared, IR, and it sort of is what happens to ultraviolet, but there's a step in the middle where the energy levels popped up. Diffracted, we haven't talked about that. That's scattering of light. Okay, so compared with the frequency of the illuminating light on a sheet of transparent plastic. Okay, so we've got light going through a piece of clear plastic. The frequency of light that is transmitted, so we're saying we know the frequency that we're starting with, that we're lighting it up with, we're shining it on the plastic, and then we look at the frequency on the outside. The frequency that's coming out, that's transmitted through the plastic, is slightly less, is the same, slightly higher, depends on the type of plastic. Well, transparent materials, transparent to visible light, it'll absorb, release, and each time it's producing a photon that looks just like the last photon. So it will have the same frequency coming through as the incident light. The incident light and the transmitted light will have the same frequency of light. So transparent materials, they absorb it, they quickly reemit it because it's not the right one to bump it all the way up, and they don't change their frequency or their energy, and energy is just based directly on the frequency. It's directly proportional. All right, the average speed of light, so this is the average speed of light, is less in A, air before entering the glass, B, in the glass, C, the air after it emerges from the other end of the glass, D, none of the above. Well, I think you should know by now that in air, whether it's before or after, it's only slightly slower than the speed of light in a vacuum. But in glass, it's slowed down significantly. So the average speed of light in glass is a bit longer because of this absorption, readmission, cycling until a photon is finally released on the other side of the glass. And this delay adds to the average speed. It adds to the total time it takes the light to get through. You increase the total time it takes through, that will decrease the average speed of the light as it's going through glass or water or diamond. So optically denser material, the more dense it is in terms of how dense it is to light, optically dense, the more of these cycles will occur. You have more particles to hit and come out of and hit and be reformed and hit and be reformed, et cetera, et cetera. So it'll just slow everything down. So the average speed in the air before and after, it's still air. It's going to be exactly the same speed in either case. All right. So opaque materials do not let visible light transmit through them. In other words, if they're opaque to us, in other words, we're looking at them and we can't see through them, then that means visible light is not going through it, because visible light has to come through from the other side through this material to reach our eyeballs. If light can't get through the material from something on the other side through the opaque material and reach our eyes, we will not be able to see through it, and that's what we call opaque. So most things around us are opaque. Opaque means it's either it's going to absorb the visible light without re-emitting it. So that means the light that's coming in from the other side or from any direction is going into it, and it's just being absorbed, like infrared would be, or like ultraviolet would be. It's absorbed in some way. It doesn't get through. Now, opaque objects, we can see opaque objects, which means some light must be bouncing off of them. So some frequencies of visible light might be, instead of being absorbed, might bounce off the object and reach our eyes, and we would see it. So if red light was the only color light that bounced off the object and it came back to our eyes, we would see that object as being red. So a red object means it absorbs every other frequency of visible light except red light. The red light is bounced off and hits our eyes, and we go, oh, that's red light. It's red object. And the same thing for blue or green or any color we see. Those are the colors of light that didn't get absorbed and they bounce back into our eye. But you'll notice it's either reflected off so that we can see it, or it's absorbed so we don't detect it at all. None of it's going through that object, and that's why we call it opaque. So examples: books, desks, chairs, walls, people, anything you can't see through is opaque to visible light. When we say opaque in this class, we're going to mean opaque to visible light, but you can discuss opaque to other frequencies of light. You might say, oh, this object is opaque to gamma rays. In other words, gamma rays can't get through it. You might have 5 feet thick of lead. That would be opaque to gamma rays. Gamma rays can't get through 5 feet wide of lead. But if you made it narrower, gamma rays can get through it. So we can talk about other wavelengths, but we're going to limit it to visible wavelengths when we talk about transparent and opaque, unless I specifically say transparent to this, opaque to this. So in opaque objects, light causes the atoms and the molecules to vibrate. Remember, vibration means kinetic energy. It's moving, and kinetic energy is just adding to the internal energy of the object. And internal energy is just another way of saying heat, the heat of the object. So it'll actually feel warmer to the touch. So let's talk a little bit about metals. Metals are opaque. You can't see through them. Light doesn't go through. Some light is absorbed, but a lot of light is reflected. And there are reasons for that. With most metals, remember, metals are very good conductors of electricity. We talked about this before. And that's because they have this sea of electrons. The atoms of the metal have loosely bound outer electrons, and they kind of donate them to the sea of electrons that surrounds the metal and holds it together. Or if there's a current, it'll start moving them, but they're still holding the atoms together in a lattice, but the electrons are moving. But even if the electrons are not moving and you just have the metal sitting there with no current going through it, it's just a piece of metal, a plate of metal, like in this photo here, the electrons are still free to wander a little bit. And that is why they're so good at conducting electricity. It's also good why they're good at conducting heat. But you have the light that will shine on the metal, and I'm going to describe the description that's given in the book, but I've talked to physicists and they've given me a somewhat different description, and I'll give you that version too. But I'm not going to test you on any details of this because I think it would be a little unfair. But light shining on the metal forces these electrons in the metal into vibrations, and that may be true. But the energy is not really absorbed. I mean, in the book they kind of suggest it is absorbed, but it's actually just bounced off completely back. It doesn't go from atom to atom like in transparent glass. You don't see that passing of the energy through. And these vibrations will emit their own light back, though they're essentially reflections that aren't changed, and they will come back and hit our eyes, and we will see the same frequencies of light that hit the outside of the metal and bounce back at us. And of course, this is more obvious when the metal is polished up so that it has a nice smooth surface. If it's not polished and it's bumpy, the light will kind of get caught in the holes and we won't see these nice shiny images. But if you smooth out the metal, it's very good at reflecting light in a very coherent direction so that we can see images like you do in this photograph. You can clearly see the man's face in the shiny metal surface. So most metals will reflect most visible light. And in fact, that's why most metals appear silver. They're essentially reflecting all the colors of the rainbow back to us, so the metal looks shiny and silver. There are a couple metals that aren't completely like that. Copper and gold are the two most obvious examples. Copper is copper color, kind of a brownish reddish orange, and gold is a golden yellow orange. And that's because they will absorb some light and reflect others, and we see them, but it's a little more complicated than you might imagine as far as seeing these colors. But those are the exceptions. They're still very shiny when they're polished up, and they reflect most of the light, and we see them as being shiny metals. We can also look at how light is different when it bounces off a dry, flat surface versus a wet surface. So when light bounces off of a dry surface, say you're standing here and there's a nice smooth dry surface over there, and light bounces off, and you can see the object, and you can see the light hitting the surface. Maybe it's the ground and it's nice and dry. Maybe it's a smooth highway and it's completely dry, and you can see it and it seems bright enough. A lot of the light has bounced back to your eye, and you can see the image of the road. But wet surfaces tend to look darker. And the reason is when the light hits them, what light would have come to your eye, and you would have said, oh, I see that object, all the light coming from it to my eye, a lot of the light bounces around inside the wet part, the water part that's on the object that's wet. And because there's bouncing, every time there's reflections in the water, some of it's absorbed. Remember I said a small percentage is absorbed, but if you have all these bouncing before it comes out and comes to your eyes, you're going to lose light every time. And as a result, the light that comes to your eye is less light. There's less intensity of light reaching your eye. And this is why every time you look at something wet, it looks darker. When I come out of the shower, my beard looks darker than if I just have it dry. And that's because when my beard is wet, the light hits it and some of the light is caught in the water and bounces around, some's absorbed. And as a result, I don't see all the colors that might be in the hairs of my beard, and everything looks darker brown or almost black on my beard until it dries out. And then the light will reflect to my eyes much better. So light reflected to your eyes means the image, less light reflected to your eye means everything will appear darker, especially with a wet surface. All right, so let's talk about shadows. Now, everybody knows what a shadow is, but let's talk a little detail about that. So if you have a thin beam of light, we call those rays. So you can think of it as a beam of waves of light or particles, photons of light. It doesn't really matter. We're just going to think of it as straight line pathways of light coming from some light source. And if something is blocking those, if something's standing in the way, if you stand in the way, or we hold an object in front of a lamp or the sun or whatever, some of that light is not going to make it past that object. That straight line path of the rays will be stopped dead. And as a result, anything on the other side of that object will have less light shining on it, and it will appear dark, and that's what a shadow is. I think we all know that. And if you have a very small source that's close by, the angle will be such that no light can essentially get around that object, and you'll get a nice sharp image of the shadow. You'll get this dark shadow that's very defined around the edges. However, if you have a different situation with light, you can sometimes get fuzzier shadows. So if you want a really sharp shadow, the two common ways to do that are to have a large light source, like the sun, really, really far away, or a smaller light source, like a lamp, that's nearby whatever you're illuminating. That will produce a sharp shadow like on the left here. But if you have the light that is such that the light, some of the light can come around, if you have like a big source of light and the light, some of the light can come around to the other side of the object, the shadow is not going to be quite as distinct. And the best way to show this is when I show you lunar eclipses. Excuse me, solar eclipses. So a large nearby source of light, if you have a really big light, you'll get a blurry shadow, and that's because the light will essentially surround the object that it's illuminating, but some of that light, depending on the angle from the light, can actually reach behind the object, and instead of having a perfect dark shadow, you'll have this mix of a dark shadow with a lighter shadow around it, and you end up with this blurry image. And we have names for this. So the dark part of a shadow is called the umbra. And so there's usually a dark part on the inner part of any shadow, no matter what the shape is. The inside of the shadow tends to be darker. And that's where no light makes it through. We call it umbra. Umbra is the Latin word for shadow. But there's usually this fuzzy area that's a little lighter. It's not quite as dark as the main shadow. And we call it a penumbra. Pen meaning one away from or less than. So a penumbra is that surrounding fuzzier shadow. So a penumbra will appear where some of the light is blocked because of the object with the rays coming from the object, but some of it gets behind the object depending on how big the light source is that's illuminating it. So you can see here, penumbra will also occurs when the light source is from something very broad, very wide light source, so that some of the light will get behind, and there won't be these dark umbra shadows. You'll have umbra shadows, but they're surrounded by a fuzz of penumbra around it. Okay, so the best way to illustrate the umbra and penumbra is by looking at a solar eclipse. So this is a situation where the moon is directly in line between the sun and the earth. In other words, the shadow of the moon will hit the earth, and we will look up in the sky and the sun will be blocked out by the moon in the way. And the reason why this even works is the sun is 400 times further away from us than the moon. But coincidentally, the sun is also 400 times wider than the moon. And because of that, the two objects in the sky look roughly the same, so that when the moon moves in front of the sun in our field of view, the moon appears to totally block the sun. They appear to be the same size. And that's why we can even have these total solar eclipses. So in the solar eclipse, you have the sun's rays, and remember, the sun is still very, very wide compared to the moon or the earth. This drawing doesn't show it, but like I said, the sun is actually 400 times wider than the moon, and over 100 times wider than the earth. So what that means is, while a lot of the light that's coming to the moon is blocked by the moon when it hits the earth, so you end up with this umbra in the middle. That's the area where all the sun's light that would reach that part of the earth is totally blocked by the moon. No light from the sun from any part of the sun, the top part, the bottom part, the left, the right, will reach the umbra if you're on that part of the earth. But the penumbra is this area that's partially shadowed by the moon, depending on where the light rays come from. So shown in this picture, you see the light rays that are blocked, but I'm going to show you here's some light rays that are not blocked. These are light rays from the sun, which is very, very wide, that actually get around the moon and light up the area around the umbra, so that instead of having one big dark shadow, you have a very dark umbra in the middle, dark shadow in the middle, surrounded by a partial shadow. And it turns out if you're in the umbra, you will see a total eclipse of the sun. The moon will be completely blocking the sun, and you will see this dark ball in front of the sun from your field of view. But if you're in the penumbra area, that surrounding area, you'll only see a partial eclipse of the sun. You'll see the moon blocking part of the sun, but some of the sun will get through, and your area will be somewhat shadowed, but not as dark as from the total eclipse. So let's look at some other diagrams here. Now, the bottom diagram is the diagram we just looked at. So a new moon is what you would have with a solar eclipse. It would be a new moon where the sun and the moon and the earth are perfectly lined up in a nice straight line. But the moon goes around the earth with one angle, and then the earth goes around the sun with a slightly different angle. So they're not usually lined up. They're not usually in exactly the same line. The moon is frequently out of line with the line between the earth and the sun. So you don't get eclipses every time there's a new moon. Every time the moon is between the earth and the sun, they're not exactly lined up. So that's kind of a rare occurrence, and depending on what part of the earth, you might have to wait years before you get to see one of these. All right, so that's the bottom situation. But more typically, it would be the typical new moon, the one right above it. So this is the third diagram down. So you have a new moon. It's called the new moon because from our point of view, we only see the unlit half of the moon. The lit half is facing away from us because of where the moon is going around the earth. And so whether we're in the lit part of the earth or the dark part of the or the night sky part of the earth, if we look up in the sky, we won't be able to see the moon because it's not going to be lit up for us to see it. The lit side is the other side. Now, I said that, you'll notice I worded it as the lit up part and the unlit part because people use the term dark side of the moon to mean the side of the moon that we never get to see. Because the moon goes around us and the moon rotates, but unfortunately it rotates at exactly the same speed that it revolves around us. And as a result, we only ever see one half of the moon. We never see the back side of the moon. So people call that the dark side of the moon. But the dark side of the moon can get lit up by the sun fairly frequently, okay? Every month, part of that month, the dark side, the side we never get to see, can be lit up. So when I say the dark side, I'm not talking about the side we never see. I'm talking about the sides unlit. So in a new moon, this is when the moon and the earth are oriented so that the moon is more or less between us and the sun, so that the lit side of the moon is the side away from us, and therefore we don't see a moon up in the sky. That's a new moon. But in other times of the month, the moon is now on the other side of the earth. It's rotating around us. It takes 1 month for the moon to go all the way around. So half a month later, 2 weeks later, it's on the other side of the earth. And typical full moon would be the top diagram here. Typically, the moon would be on the other side of the earth. And so the side that's totally lit up of the moon is the side that we can look at when it's dark here. When we have a night sky, the side that's not facing the Earth, we can look up and we can see the moon, and so we would be looking from the dark part of the Earth, the night sky of the Earth, and looking up at the moon, and we'd see all of the moon would be lit up from our point of view. That's a typical full moon. It's called a full moon because we get to see the whole lit side of the moon. There's always a lit side of the moon, but sometimes we don't get to see it. When it's on the other side, we call it a new moon. When we get to see it, it's called a full moon. So we get to see the moon lit up, but again, the moon is not always in a perfect line with the Earth. When that does happen, which happens a couple times a year actually, so maybe 1 out of every 6 full moons, the moon is a little bit lined up with the Earth, and now the Earth is between the moon and the sun, and that's the second diagram here where it says full moon with a lunar eclipse. And now the Earth is blocking sunlight from the moon, but the Earth is considerably bigger than the moon. It's about 3.7 times wider than the moon is. So because of that, we completely block the moon during a lunar eclipse, so all of the shadow is an umbra. There is no penumbra in a lunar eclipse because sunlight cannot get around the Earth to reach the moon on the edges. There just isn't. So the moon is completely turned dark. It appears reddish to us in the sky. You ever get a chance, go out and watch a lunar eclipse if it's visible to you sometime. They're kind of cool to watch, and they last longer than a solar eclipse. Solar eclipse can never last longer than 7 minutes for any point on Earth, but a lunar eclipse can last considerably longer, and you can watch it. All right, so in the lunar eclipse, the Earth is making a shadow on the moon. In a solar eclipse, the moon is making a shadow on the Earth, but it's not all umbra. There's a penumbra. So that's the big difference here, and obviously it looks different to us in the sky because when we're looking at a solar eclipse, the sun is totally blocked by the moon. When we're looking at a lunar eclipse, we're just looking at a darkened moon because we're looking at the moon and it's darker because not as much sunlight is hitting it. All right, so let's talk about the structure of the human eye. The human eye is really an exquisite piece of machinery in a way to allow us to detect wavelengths of visible light. And it has many different parts to it, but it's really quite a remarkable device. And as light will enter the eye, so it'll come in past the cornea, that's the kind of shield, the clear shield in front of our eye, the light will come through, and some of the light will be bent, what we call refracted. You'll learn about this more in chapter 28. It starts to get focused by the cornea, and then the lens will do the rest of the focusing. And the light will pass through the cornea and then through a hole, and that hole is right there. That's the pupil, and that will allow the light to get into the lens. So I'm going to go back here. So a lot of the focusing will happen, the bending of the light will happen in the cornea, but the light then goes through that space in front of the lens called the pupil. That's the hole. That's the dark part of our eyes. When we look at our eyes, we see the colored ring. That's the iris, and the hole in the middle is the hole that allows light to get into the lens of our eye. And so the iris is the colored part. It's called the iris because the ancient Greek goddess of the rainbow was named Iris. So because we have all these colors in our eyes, we named it the iris, the colored part of our eye. So we have the pupil where the light will actually penetrate through the cornea, and then there'll be a space for the light to come through into the lens. It's basically coming in within the hole of the ring of the iris. So the light goes through the iris, through the pupil that's in the center of the iris, and will go in. And the iris will contract or expand and make the pupil, the hole of the pupil, bigger or smaller depending on how much light is available. So if you're in a room that's very dark, your iris will spread out and make itself as small as possible to make the hole, the pupil, as big as possible to allow the most amount of light into your eye so that you can see better in the dark. And this is why you always have to get used to, it's one of the reasons you have to get used to when you walk in a dark room, you have to wait for your eyes to adjust, for your pupils to enlarge, to allow more light into your eyes so that you can go, oh, now I can see. There's enough light reaching the back of my eye and the retina and letting me know what images are here. But besides the available light, your pupils may be also affected by, among other things, genetics, disease, injury, and the most well-known would be drugs. There are a lot of drugs that when you're on them, it will dilate your pupils. It'll make your pupils much, much bigger, so your irises will become these thin bands of color with a giant black spot in the middle. Your pupils are huge when you're on certain legal medications and certain illegal medications. Okay, so it will then go through the lens, and the lens is basically made of proteins that act, they're kind of in a crystal form, and they act to focus light that goes through the lens. So light is already partially focused through the cornea, and then the lens really fine-tunes the focusing so that any light, any images of light that are coming through the lens will actually focus on the back here, on the back side of the eye, and that's what we call the retina. The whole back side is called the retina. And I know you've heard that term. You may not have known exactly what the retina is. Now, filling the eyeball between the lens and the retina is this jelly-like liquid that's referred to as the vitreous humor. Vitreous means glassy, and humor in this case means fluid. So it's this glassy fluid that fills the eyeball, and so the light goes through that and reaches the retina where it's detected. So light will pass to the retina, and the retina covers about 2/3 of the back of your eyeball. I recently had my retinas photographed because I had a blood vessel burst in my retina, so I was actually seeing the blood flowing around in my left eyeball. It went away eventually, so everything's fine, but they took photos so I could actually see what the retina looks like. It's quite remarkable to see the blood vessels that are all flowing through the retina to feed the retina. All right, so you have a wide retina that's covering the whole back of the eyeball, and that's your field of vision. That's where images are collected by the cells in the retina, and then that information is passed to the brain. So the light has to focus directly on the retina. If it focuses in front of the retina, or if it would theoretically focus behind the retina, you have nearsightedness, farsightedness, because it's focusing in the wrong place, and we use corrective lenses in order to make it focus in the right place on the back of our retina so we can see images. So the retina is not uniform, though. It's not the same all the way through the retina. The center of the retina, which I have circled with a red oval here, is called the macula. And this is really the best part of your vision. This is where you get the best part of your vision. You don't want to destroy the macula. That's the center of your field of view. No matter where you're turning your head, the center of your field of view is due to the light interacting in the macula part of the retina. And the very center of the macula, there's a little depression there. That is called the fovea. And that's like the best part of your color vision. So the fovea will give the light that hits the very center of your field of view. You have the best color vision right there. And we'll talk about why that is in a second. So now, in addition, you have this retina, which essentially becomes the optic nerve. It kind of morphs and becomes the optic nerve. It makes this tissue that leaves the back of the eye and goes, and the optic nerve is really an extension of your brain. It's directly connected to your brain. It's actually in some ways considered part of your brain. The space in between there, where it says blind spot, there's actually blood vessels that go in there. There's the retinal artery and the retinal vein that feed the nerve. But because this is where the optic nerve is attached to the retina, the retina can't pick up light there. It can't detect light there because it's not holding the cells that detect light. It's a blind spot. It's a spot you can't see. And it's close to the center of your vision. It's a little off, depending on where you're looking. But you might say, well, wait a minute, I can see everything. Why, what do you mean there's a blind spot in my eye? Well, you think you can see everything, but the part of your vision, if you're looking forward, the blind spot is a little bit away from the center of your vision. So whenever you move your vision, you're always using the center of your vision. But just to the side, if you're looking forward, just to the side of that is where the optic nerve goes into your retina, and you can't see anything there. You're totally blind, but your brain looks at all the images around it and fills it in for you. So when you're looking at something, especially like a wall, and you don't see any missing spots, that's because your brain looked at the rest of the wall and said, okay, everything else looks like this. I'll just fill that in for your brain, and you think you're seeing a nice solid image with no blank spot anywhere. And this will happen everywhere. And you can prove this to yourself. I think there might even be a diagram in the book where if you move your eye in close enough and stare at one image, you'll notice this other image will eventually disappear because your brain doesn't know what to replace that with. And that's how you can tell that there is a blind spot in your field of vision. So how is this actually working? How is the retina actually working? Well, the retina has all these different cells sticking out, and there are two main categories of cells called photoreceptor cells. These are cells that receive light, and they have specific proteins in them that actually the proteins have a derivative of vitamin A on them, retinol. And what happens is light hits the retinol that's part of the protein that's attached to the protein, and the molecule retinol actually will bend in a different way. So the whole protein will bend, and this change in the shape of the protein will turn on other chemical switches that become certain signals that go to the nerves, that go through your optic nerve and to your brain, and your brain will go, oh, light must have hit that, and I'll detect it as light. And the two main categories of cell are the rods. These are the cells we use to see essentially our black and white vision. These allow us to see in dim light and dark light. So that's why when you're looking in dark light, you barely see any color because you're using the rods to see at that point. And the rods are really good at detecting very, very low amounts of light. And they tend to be not right in the dead center in the fovea. They tend to be very high right around the foveas of both of your eyes. So you have really good vision close to the center of your field of vision. But right in the very center, you have different cells called cones. And cones are what give you your color vision. And there are three different kinds of proteins in these cone cells that allow you to see red, green, and blue light. And the combinations, your brain will combine the information from the red, green, and blue light so that you see all the different colors. And when we learn about colors in the next unit, you'll see why that is. So cones are very, very dense right in the center of the retina at the fovea, okay, right there. And there are almost no rods right in the center. It's tons of cones. And then immediately after that, there are barely any cones for the rest of it. So you really only have color vision in the very center of your field of view. So when you're looking at things, you think you see color everywhere, but that's because you're moving your eyes all around. But really, you only see the color vision in the center of your field of view. And when you move your eyes, you see all that color as you move them. But, your color vision decays significantly on the sides. So like I said, there are three different kinds of three different types of receptors in the cones. And these are activated by different frequencies of light. The ones that are activated by low frequencies of light are the red color receptors. The intermediate ones are the green, and the highest frequencies of light in the visible range are your blues and violets. It's actually better for the blue than it is for violet, and that's why we actually see blue a little bit better than we do violet. So these receptors the information from those will combine to give us all the colors that we can see. All right, so we've talked a little bit about the structure of the eye. Let's talk about what the eye can do and some of the funny things that it does that we don't necessarily want it to do. So although our vision is really poor out of the corners of our eye, we have peripheral vision. It's usually relatively good, but it's not anywhere near as good as the center of our field of view. But we have lots of rods we have a ton of rods, close to the center, and then they kind of out. But we still have enough rods on the side of our view so that if we're looking, we can see not quite 180 degrees, maybe a little bit less. I'm guessing 150 degrees angle range. So we can see to the sides if we're looking forward. We'll notice things to the side. You can always just take your arm, look forward, and see when your arm disappears. Mine disappears about here. And that gives you an idea of your peripheral vision field of view. but we still have enough rods there to detect light so that if anything moves on the side, we will immediately respond. We'll notice something on the side. And obviously, for evolutionary reasons, this is something that would have protected us from wild animals that might have attacked us, or some other danger that's coming in from the side if we're not looking directly in that direction. All right. So let's talk about some of the weird optical illusions that the eye can have. And the rest of these slides are really for fun. I'm not going to test you directly on this, except for one possible little factoid here. So let's look at this. There are two rectangles of gray, and they each have varying gray color. And the question is, which one's brighter? Now, you might look at this and go, well, the left one's dark and the right one is lighter. And to me, that's what it looks like. The right one looks considerably lighter than the dark one. But this is actually an illusion. And so this illusion stems from the fact that the eye can see an enormous range of brightness. We can see objects that are super, super dim, super, super dark, and objects that are 500 million, that is 500 million times brighter. We're able to see both of those with our eyes without damaging our eyes. If we go too bright, obviously we'll damage our eyes. You don't want to look directly in the sun for obvious reasons. And part of the reason we're able to see super, super dim things and super, super bright things, sometimes right next to each other or near each other, is because of something called lateral inhibition. Lateral inhibition is this function that the brain does that, in concert with the nerves from the eye, that when you see a bright image, your brain will say, okay, take it down a little bit, so that we're not seeing everything so bright that we can't see the surrounding areas around it. And it kind of smooths out the brightness that we see so that we're able to see super, super dark things and super, super bright things and not have the bright things completely overwhelming our field of view. So these two rectangles are part of an example of what that will actually do to the way we perceive things. These two rectangles are absolutely identical. Now, I know for a fact they're identical because I took the original drawing, deleted one of the two rectangles, and just duplicated a rectangle and made a second one exactly the same. I literally did a copy and paste right next to it. They are absolutely identical rectangles. The trick is the left side of each rectangle is brighter and the right side of each rectangle is darker. And this chart below it shows you the relative brightness as you go from left to right. It's bright, it comes down, and then there's the border between the two, and then suddenly it's bright again and comes down. And our eyes look at this and they say, oh, the right one is bright and the left one is dark. And one of the reasons our eyes do this, besides the fact that we want to have this enormous dynamic range of how bright objects we can see from super dim to super bright without being overwhelmed, but it also allows us to see borders very, very clearly. Our eyes are really good at making out division lines between objects or shades or patterns, and because of this, our brain exaggerates the images between two images that are next to each other, and we see this very sharp border between them, and that is a function of this lateral inhibition. And just to prove to you these really are the same rectangles, hopefully putting a line in the middle to blot out the darkest part of the left rectangle and the brightest part of the right rectangle, you can start to see the rectangles are looking much more like each other. If you actually take this and move it over, you'll see they superimpose right on each other. They're exactly the same color range. All right, so here's some optical illusions. Obviously, I'm not going to quiz you on these, but they're cool to look at. A lot of these are in the book. Some I added one or two that aren't in here. So partly because of lateral inhibition, partly the way we detect light. If we look at this top image, the question is the slanted line, the diagonal line, really broken? It looks jagged because you have these horizontal lines through it, but is it actually jagged? And then the bottom diagram, we have a stack of dashes, and then we have another stack of dashes that's pushed over to the side, so it's tilting. And the question is, which side has longer dashes? And you probably already guessed that these dashes are about the same size. So let's look at the two images. I've got a diagonal line in red on the top here that you can clearly see is straight. It's just dotted line. And I'm going to move that over, and you can see it lines up perfectly with the black line that was in the original drawing. So it's straight, totally straight. And as far as the image on the bottom goes, I have a little red line that I created, and I duplicated it and put it on the top of each of the stacks. And you can see they both match their respective stack. They're exactly the same width, even though they look narrower with the stack that's slanted. And that's an illusion from our eyes, thinking that the width is different because of the orientation of the dash. So this next illusion, this is called the Hermann grid. This was created by Ludemar Hermann in 1870. This whole field of studying optical illusions really started in the mid to late 1800s, became very popular. So Ludemar Hermann created this illusion, and this is an illusion where if you look at the intersections of the white lines between the black boxes, you will see, if you stare right at an intersection, it will appear white, which is the way it is, but your peripheral vision will detect black spots until you look at them. So if you try to count the black spots, they keep disappearing on you because those are actually an illusion. And this was originally thought to be an example of the lateral inhibition that I just mentioned, but recent evidence has actually suggested it's something else, and people are still trying to figure out the actual reasons for a lot of these illusions. This top left drawing and the bottom right drawing, these are classic drawings from M.C. Escher. He would draw these optical illusions which look normal at first glance, and then you realize that they're impossible structures. If you look at the screws and the screw holes on the left, you realize the bolts here that would screw in. It looks initially like 3 bolts, but then when you start staring at it, you realize it's not exactly what you think you see. And if you look at the holes that they go through, you have a hard time reconciling in your brain whether those holes are on the left, on the right, on the inside surface, or on the outside surface of this rectangle. And then the cube on the right, it's a little more obvious that it's something very strange that couldn't exist, where you have something that should be in the back is in the front, and something that should be in the front is partly in the back. So these are classic M.C. Escher drawings, and he has a huge collection of these. I highly recommend it, especially if you like art and if you like optical illusions. Escher's work is really astounding to look at. So here are a couple classic illusions. Is the hat taller than the brim is wide? So you're looking at it, and human eyes are good at measuring height roughly with their eyeball, but they're better at measuring vertical lengths than they are at horizontal lengths. So we have a hard time comparing these two. And then the other illusion is this yield sign that says Paris in the spring. But is that what you read? And most people will read Paris in the spring. So let's look at the first one. We have the hat. So I took the same hat, and you can see the body of the hat, the brim of the hat and the body of the hat are about the same size. The width of the brim and the height of the hat are essentially the same dimension, even though to look at the top one, it would seem that it's much taller than it is wide. We're not very good at comparing those. That's why it's good to pull out a ruler for that sort of comparison. Paris in the spring, if you look at it carefully, you realize the is repeated, and a lot of people miss this the very first time they see it. This is an old one, so you may have seen this before. It might not surprise you at all. And this image here is called the Zollner illusion, created by Johann Zollner in 1860. And some people, when they look at these diagonal lines that have little cross hatches of short lines going through them in alternating angled directions, some people actually, if they stare at it long enough, they see the lines kind of moving, almost as if this was a short movie instead of a still image. But it's actually a still image. And then the other thing is people will assume, looking at the diagonal lines, that they're not all parallel, just because of the way the cross hatchings are lined up. They don't look like they're actually parallel. So I created these red lines on the right here, and you can see they clearly are parallel. I'm just going to slide it over, and you can see that they match the drawing perfectly. And And you can now see that the lines, in fact, are perfectly parallel. Another illusion. And then this is a very similar illusion where you have alternating rows of crooked tiles here. And the question is, are the layers actually crooked? Are they alternating angles up and tilting up, tilting down? But again, if you take straight lines that are clearly flat, clearly parallel, and you slide them right across, you can see without a shadow of a doubt that they are perfectly parallel. And with that, we'll stop here.